writes a letter home to his mother. He writes it from the Palisades in New Jersey, right above where his bridge is going to be. And he's imagining this bridge when he gets to the United States in 1904. And here's the cover of the book, Die Brückenbau in den Vereinigten Staaten Amerikas. And it's a classic text and the way Ritter saw American bridges. And so as this teacher teaching the rigorous mathematical basis for engineering, at the same time he's teaching the practice. He's telling how designs are made today and just in the recent past, and he's bringing his students into the excitement of the actual building of these bridges. And that's what stimulated them, definitely. It wasn't just exercises in stick diagrams and formulas. Next slide. This is one of the books. Ritter wrote 4 books. This is called The Applications of Graphic Statics to Arches, bogen. And Amann, next slide, would write a groundbreaking article. This is the calculations in Ritter's book for a 2-hinged steel arch. And next slide, these are calculations made by Amann, and you see it's the same calculation of the stresses in a piece up in here, how he derives at that piece through this graphic statics, which is a way of visualizing the form as you are making an analysis. Something that was invented essentially in the school in Switzerland by Ritter's teacher, and Ritter taught that to his students, a combination of visualization and analysis. And next slide is the bridge, the Bayonne Bridge of 1931, which was designed by Ottmar Amann. That's what these calculations are for, which comes right out of his studies with Wilhelm Ritter. This was the longest spanning arch in the world when Amann designed and supervised the building of it. And next slide is the George Washington Bridge, which was the longest spanning bridge by a factor of 2 of any type in the world when it was completed in 1931. And these are the first 2 bridges that Amann designed on his own. Pretty good start for a career. And he went on to design all the major bridges around New York, ending up, next slide, with the Verrazzano Bridge. And this is his last bridge, which he completed at the age of 84. So that gives us all hope, you see, that later on we may. Anyway, this picture is, of course, a stamp. It's a Swiss stamp commemorating the 100th anniversary of Amann's birth in 1879, and it has on it the Verrazzano Bridge. Now, the Swiss are noted for never putting the works of other countries on their stamps. So it's clear that they view all those New York bridges as Swiss bridges exported. They simply didn't need them in their little country, and so they sent them to us where we could use them. In fact, when this exhibition went to Zurich in 2005, the logo, the poster for the exhibition showed the Lake of Zurich, and the Lake of Zurich was spanned by the Verrazzano Bridge, the George Washington Bridge, the Bayonne Bridge, the Bronx Whitestone Bridge, the Triberto Bridge, and the Thog's Neck Bridge. So they brought the bridges back, you see, and that's what they said. Swiss bridges return. So the exhibition was supposed to do that. Next slide. Well, here they are, that you'll see them in the exhibition, the Bayonne Bridge and the George Washington Bridge. And the young man who took over the task of designing and building them, next slide, is seen here on the right, Josh White. Josh White was a junior when he did this. He is now working on his PhD at Stanford. He will be a spectacular teacher when he finishes. And this is all done in a 3-dimensional milling machine controlled by a computer. And so he had to design the computer program to put into the machine. And these parts, each part was done, each half of this was done. And next slide. And then they were connected together by a device which was designed by our master machinist. They couldn't have done this work without the master machinist, the laboratory director we had. So although they did all the work themselves, they needed help for sure, because the faculty, of course, are totally incompetent in such things, and they were able to get that kind of help that they needed. Next slide. And here is Joe Vacatoro and Josh putting finishing touches on this. And now they decided for this model to use brass. because it is easy to work. They could braze it and connect it more easily than they could with steel. And so that was the choice. And of course, it makes a very elegant model, as you will see. Next slide. And here he is again, explaining it to those who don't understand such things in its nearly completed form. And next slide is another view of this model, which is down there in the exhibition, down there, here, there, wherever it is, nearby here in the exhibition. Next slide. All right, now we come to the second pair of designers and their teacher, Pierre Laude. So here's Laude. Now what we have, and what the only really original artifact that is in the exhibition are eight notebooks of Heinz Easler, which record all of Pierre Laude's lectures. It is the most marvelous set of lecture recordings of anything I know of at all. Because Easler is himself an artist. He also does sketching and drawing very beautifully. And the notebooks are very elegantly done, and they record Laude in this teaching mode of strong on the mathematics, but always interspersing within it the aesthetics. For instance, here's what we call in America the flat slab. It's a slab with columns supporting it, with capitals that distribute the big load from the deck down into the columns. And you see he shows different ways of doing that. If you look at an American text, there's only one way shown normally. And that's assumed to be the right way. That's this way. And what Laude is saying is, well, okay, this way is a little bit cheaper. He says billiger, cheaper to build. He's wrong about that, actually, but he says that. And then he says, however, this is aesthetically and statically much better, and it's Maillart's design. So he's teaching Maillart's designs to Easler and to Men. And then he's giving this throughout. There's this intermixture of analysis, mathematical work, and aesthetic discussions. Next slide. And here is an example of one of Maillart's designs. This is for a filter plant, a water filter plant in Rorschach. There is a city in Switzerland called Rorschach. I don't know if any of you ever heard of the Rorschach test. How many know the Rorschach test? Oh, good. Okay, so you know what that is. Well, if you drew that based on your Rorschach test, then you would be a great structural engineer. In any case, we were happy to find this, to picture this when they were cleaning the place out, and so the water was no water in it, but normally it would be filled with water way up to about here. So, but it shows you the elegance of the columns and of the flared capitals at the top. You see, whereas the American system, the drop panel system, a horrendous system, technically it's wrong, and it's a pure copy of a Doric column. That's how it came into being. It didn't come into being because somebody said this was the best. It's because they wanted it to look like something Greek in 1905 when they first introduced it. Next slide. Now we come to Easler. Heinz Easler, the first student we want to talk about of Pierre Laude. And what you see is Easler over there, standing there with a big grin on his face and a whole bunch of laminated wooden arches, which are all battered up here, the edges. And they're battered up because they're reused many, many times. And he's building these thin shell roofs, which are the major expense is the formwork that holds them up before the concrete is hard enough to take away. And so what Easler is doing is he is using very expensive laminated wooden arches, but he is designing in such a way that he can keep reusing them many, many times. So the cost on any project is very low, even for these expensive ones. So he puts these up, here you see them, and he has a light metal scaffolding. And then on top of that are slats that are just battered in place. Next slide. And here you see the workers on top of the slats are placing foam board, which is insulation. And on top of that, there'll be reinforcing mesh and then concrete. And then they will take away the scaffolding and the laminated arches and the slats. They will leave the foam board there anchored into the concrete because that's insulation. That means now what he's doing is, as we will see, he is designing a concrete system with such a form that there is no tension stress in it due to its own load. And then he is putting the insulation there so that through the concrete thickness, the concrete will have only the heat of the outdoors. So it'll have no thermal gradients. So there is no way that concrete will crack. Since it won't crack, it means it won't leak. And therefore, Easler never puts any roofing on top of his concrete structures. They're all just bare concrete. This is a harsh Swiss environment, and they never leak. Next slide. This shows you the inside of it, where the foam board is what you really see on the inside. Next slide. But he wasn't satisfied with these forms. This is the basic form he chose. What he's doing here is taking a piece of cloth and attaching it to a frame, pouring a wet plastic on top, and then releasing that. And the next slide shows that it's hanging. Now that is hanging, and that is completely flexible. The only thing it can support is pull, is tension. But if you tried to push it, it would just squash right up, or twist it, or bend it. Has no resistance at all until the plastic is hardened. So it stays there in that form. So it is the form of this material under gravity. And then it hardens, and then he turns it, next slide, he turns it over, and now he has a structure which is in pure compression. So he has it in pure compression, and not only that, but he can see the edges turn up to stiffen it, and they show the thinness of the structure, which he wants to do aesthetically. And therefore he has a structure now which is perfect for him under gravity loading. And it has no need then for any roofing material. And roofing material is very expensive, and particularly when people try to do it on thin shells, it can be more expensive than the structure itself. Next slide. And so then he builds it. Here are the laminated wooden arches, and then the next slide shows the structure completed, and you see how thin it is expressed at the edges, thickens at the very corners where the forces come together. And so he builds hundreds of shells like this, which require no roofing, so they're competitive in price, and this covers a swimming pool. Next slide. And this one, the Seekley building, these are standard. He does many like this out of the same forming. This is more complicated. It was a seven-point supported shell, hung the same way. He got the form that way. He didn't build it that way. He didn't build 160 feet of cloth and then turn it over for the structure. He just builds that at small scale, obviously, but gets the form that way, which he then uses to build it full scale. And so this one, again, it has about 160 feet in span. It's 7-point supports, very complicated. It's quite thin, as you can see, all expressed. It doesn't have a geometric form. It's a form that is caused by physics, not mathematics. Next slide. And here are some covered tennis courts that he does. This is the Heim tennis courts. He did 4 of these. He made each one slightly different as a kind of an experiment, and the one which deflected the least when it was the scaffolding was removed is the form he then used as a standard. For the rest of the time, he did many of these covered tennis court shells. This is a difficult one because it's more of a rectangular than a square form, much more difficult from the point of view of buckling of this kind of shell. Next slide.